Hi,
Oh, they
everyone.
already pressed. Okay.
All ready
Hello,
for us.
guys.
Okay. And I just wanted to first of all welcome everyone to our show. Can I first double check that you guys can hear us? If you can hear us, please send a message to chat relay saying that you can hear what's going on. The way to chat in this whole live stream is to send messages to chat relay, and then they'll appear here on the screen. Yes. Okay, very good. Well, with that, let me introduce. Hi, I'm Po-Shen Loh. Welcome to our stream. Welcome to our YouTube channel. And we're really happy today to collaborate with Math League. Math League is an interesting competition where they have contests basically every month. They have about six of them through the year, and it's a great way to go and practice doing hard math problems. Hard means things that you don't know how to do before. Fun fact, I was actually visiting the founder and leader of Math League at his home in Bali, Indonesia, earlier this month. So Math League is based there. Over there, they don't have that cold weather. Over here in the United States right now, we have some pretty cold weather. Well, with that, let me introduce the two hosts for today. I won't be doing the stream. Instead, we have two incredible people. We have Gloria and we have Thomas. Gloria, could you just make a sound so that you take over the screen?
Yeah, sure. Hey guys, I'm Gloria.
Wow,
Really excited to be here.
great. And then Thomas, could you also make a sound and take over the screen?
Yep, my name is Thomas. Hello, guys.
Cool. Okay. And then, as you can see, the way to interact with everyone through this is to send messages through chat relay. Also, you can see they've got icebreakers ready for you. And with that, I'm going to toss it over to Gloria to take it off and introduce Thomas and each other and then dive in.
All right. Thanks, Professor Lowe. So, first of all, it's really weird. I'm some random person you're seeing on a screen right now. So, to make it less random, we've prepared an awesome, awesome icebreaker. Very, very interesting. I'm sure you guys will absolutely love it. And it's a very, very classic question. Which came first, the chicken or the egg? What do you think, Thomas?
Actually, I was the one who came up with the icebreaker, so I had like a premeditated answer. My answer is definitely the egg, because, um, all right, the argument is a bit technical, but if you think about it, like, if you think about the evolution process from a creature that's not a chicken to a creature that is a chicken, like, if you gave it an index, say 0 was the starting point, and 1 was the point where if you cross it, then you're a chicken. Uh, but if you look at it, it's gonna be like a step function. So this is the first creature during its life period, it's the same creature because you can't just mutate. And then once you lay an egg, it mutates a little, so it jumps. Okay, and then it lives its life, and then lays another egg, it jumps, and then like as a step function, it steps up a bit by bit, and then at the end, there's gonna be a little egg that's already on the threshold of chicken, and that was my first chicken, which was the form of an egg. So yeah, that's what I think.
Yeah, wait, I completely agree with you. But I think when it comes down to this question, a lot of people think like the physical chicken, like the ones you eat at KFC or something. But, what if it was the idea of a chicken, right? Because in the beginning, there were dinosaurs and whatnot. And maybe those dinosaurs had a dream of becoming a chicken. And maybe, the bacteria even before that, they had dreams about becoming chickens. You don't know what bacteria are thinking, maybe they have like this really, really awesome dream of becoming a chicken. So maybe the chicken came before an egg. You never know.
Well, for dinosaurs, I think they would probably be dreaming about eating chickens instead of being a chicken, but I don't know. What does chat think?
What do you guys think? Does this kind of, oh no, oh man. Think looks like
Chickens,
everyone says eggs.
dreams of chickens, chickens evolved from dinos. I mean, maybe, yeah, I think birds did come from dinosaurs. The chicken is closely related to the dino. Egg, okay, so yeah, majority is in support of me.
Okay. Well, we don't know history, so I still believe that, chickens could have come first, especially all of you guys chickens. Wait, no. All of y'all chicken lovers. I mean, like even though, eggs might have come first, like physically, the idea of a chicken may have, came first. So I think it's really, really important to specify. But before that, Thomas, they're all they're saying are two strangers on a screen. So I think we should introduce ourselves first. And so
Hmm.
now I'm going to introduce my awesome, awesome partner today, Thomas. So Thomas is a really, really cool guy. He's an Amy qualifier, but not only that, he's also a useful honorable mention. And so USFO is this really, really elite and prestigious and competitive physics competition. And so he got honorable mention in that, which is really, really hard thing. It's a really, really hard thing to do. And he's also a physics bowl national gold medalist, which is really, really cool. And additionally, he's also I think I might mispronounce this, but an Yes T Yao finalist, which is also really, really cool. And in his free time, he loves dabbling in computer science, listening to EDM, as well as cycling and donuts. So let's all say hi to Thomas. Hey, Thomas.
Hello, guys. Okay, so the person who just introduced me, she's called Gloria. She has an impressive history in math competitions, which includes qualifying for Amy since the seventh grade, which is actually really impressive because she's qualified for a few years consecutively now. She was a two-time Texas Math Counts state participant, and she's also a really good speaker because she was the third best speaker at the 2023 National MSTOC for LD. And then she was an octo finalist at the National MSTOK for LD. She loves poetry, reading, and she enjoys K-pop. Really cool person.
Wow, thank you for
Okay.
that awesome, awesome introduction, Thomas. Oh, yeah, it's K-pop, not K-pop. I think someone in chat, yeah, and K-pop, K-pop is a bop, but it's not K-pop, it's K-pop. Kind of confusing, I know. All right. So I know all of you guys are just really, really, really eager math people. Here, I don't like to call people mathematicians because I think what we do, working with math is quite frankly, basically magic. So here, we're all mathemagicians. And so without further ado, let's get started on the first exciting math spell or math problem of the hour, which is this problem. All right, so what is the positive difference between the products 9 times 9 and 6 times 7? Thomas, how should we proceed with this?
Well, I mean, by reflex, I just want to calculate 9 times 9 and 6 times 7 and just subtract them because, it's the first problem. You got 29 more to go. You don't want to overcomplicate things. So fast and simple, I think, is the key here. So, okay, 9 times 9 is what?
9
39.
times 9.
Are you sure, guys?
Okay. It looks like a lot of people are sending in answers in the chat. So, yeah, keep it up. We always love seeing your awesome, awesome ideas and answers. And it looks like the overwhelming general consensus is 81. So, yes, and you guys are in fact right. 9 times 9 is 81. Now, on to the next multiplication problem, which is 6 times 7. And what do we think 6 times 7 is?
Hint, it's
Ooh,
not 35.
ooh,
Yes,
okay.
it's 42. Great job, guys. Okay, so now the final step, don't get it wrong. What's 81 minus 42?
Ooh, okay. 81 minus 42. Here's a hint. It's not 81. Hmm.
That was a
Okay.
helpful hint.
I know, very, very helpful. Definitely the deciding factor of figuring out this answer. And it looks like, again, the general consensus is 39. Ooh, okay. And so 81 minus 42 is indeed 39. But who knows, maybe the world decided to somehow change 81 minus 42 into 81. So to be completely sure, let's check the answer. And it indeed is 39. So apparently the world didn't mess with us. Now on to the next exciting problem. Ooh, okay, so now we're dealing with variables. Thomas, do you want to start this one off for us?
Sure. So, I mean, at first glance, what's the first like reflex you have when you see this problem? So, Well, x squared over x minus 1 equals 4. This is like a condition for x. So there's two things that's possible. Either I can completely solve for the value of x, and get rid of all ambiguity and just calculate x squared minus 1, since I can solve for x. Or I somehow try to manipulate this condition without explicitly solving for x. But if you like think about it carefully, it's actually quite easy to explicitly solve for x. And this is because if you multiply both sides by x minus 1, you'll get a pretty familiar quadratic, which can be solved easily. So if you do x squared, if you multiply both sides by x minus 1, you'll get x squared equals 4 times x minus 1, which is x squared equals 4x minus 4, which is x squared minus 4x plus 4 equals 0. And can you solve this quadratic without using the quadratic formula? Yes.
Mm.
Okay. So some people might already see that this is a perfect square, so I don't need to use the quadratic formula. I just factor it as x minus 2 squares equals 0. So, the square of a number equals 0, so that number has to be 0. X minus 2 must be 0, so x must be 2. So x squared minus 1 is 4 minus 1, which is 3. Okay, yeah. Quadratics are not fun. Well, some quadratics are. The neat ones are. The messy ones are not.
Ooh,
Okay.
okay.
And the answer is 3 indeed.
All right. Now, if you guys were paying attention, you might have noticed that the answer was three on question three. Very, very interesting relationship. I wonder if it's going to be the same for future problems, but we'll never know unless we continue on with our amazing and fun math journey for today. So, on to the next problem. Okay. Ooh. So now we have a guy named Paul. And so Paul randomly chooses a prime number p between 1 and 100 inclusive. What is the probability that the fraction 1 over p can be expressed as a finite decimal? Now express your answer as a common fraction. So before we dive into the math part, there's a really, really important part called English that we need to fully understand. And so there are two keywords here. And so the first keyword is inclusive. Inclusive means that between 1 and 100, we're still going to count 1 and 100. So we're going to be looking at the numbers 1, 2, 3, 4, 5, yada, 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 all the way up to 100. And then the next keyword is finite. So finite means not repeating. If you guys have, I'm sure you guys have, in number sense in Math League, seen something maybe like 1 over 3, in which the decimal version of that is 0.3333, repeating on forever. Now, finite is the opposite, which means it ends. So something like 1 over fourth, which equals to 0.25, now that would be finite. So, Thomas, how do we find a finite decimal? How do we solve this problem? Because there's like 100 numbers to choose from, right?
Okay, so that's actually what you think. There is 100 numbers to choose from. But if you like, all right, so first of all, if you try writing, okay, so first of all, let's just list a few primes. So the smallest prime is 2. Okay, 1 is not a prime. 2, 3, uh, 4 is not a prime, 5, 7, and then yada yada yada. Okay, so if we do 1 over 2, that's 0.5. That's definitely finite. Okay, 1 over 3, that's 0.3 continued. That's not. 1 over 5, that's 0.2. That's finite. 1 over 7, that's uh that's a decimal with like a long period, but it's repeating, so that means it goes on infinitely. And for all the other primes, they all go on infinitely. And actually, you can see this because if you think about finite, what does it mean for a decimal to be finite? It means that if I write a few digits, it will eventually end somewhere. Like it won't go on forever. So what this means is that if I move this decimal point all the way down by multiplying tens, then I'll get an integer. So let x be any, okay, let's look at any finite decimal. We're gonna use x to denote it. So I there must be a power of 10 that I can use to multiply x to get some integer, okay? Some integer. Okay, but I mean, this means that when you have a 1 over something, 1 over p in the form, this some integer must be 1 because if you multiply all the other stuff, you will have to get a 1. So this will mean that your x has to have a power of 2 or 5. So the only primes that actually work here are 2 and 5. And actually all the other primes are infinite. So if you count all the primes from 1 to 100, and this is kind of the hard part, uh, there are actually exactly 25 primes. So if you count it, if you're able to count it fastly and accurately, then probability, which is just the number of wanted outcomes over the number of total outcomes. So the two primes I want are 2 and 5, which is 2. There are 25 primes in total. So if you divide that, you get 2 over 25 as your answer. So actually, guys, do not uh, count the primes wrong, or else this problem will actually get you a incorrect answer.
Yeah. And so, thank you, Thomas, for that 10 out of 10 explanation. Or should I say 100 or out of 100? Or maybe I should say 25 out of 25 explanation. It was very technical and really, really good. But for some of you guys who may have been a little lost, essentially what Thomas was saying is that kind of in fractions, we're just doing division. So 1 over 2 is essentially just 1 divided by 2 or and 1 over 3 is just 1 divided by 3. And so if we kind of expand it, right, we could say 1 over 2 is equal to 10 over 220 is equal to 100 over 200. So essentially, the only way we can get a finite decimal is if the denominator divides into the numerator. And so, like many of you guys have already been saying in chat, the only two numbers that work are 2 and 5 because the only divisors of 10, prime divisors of 10, 100, 1000, and etc. are 2 and 5. And so that's just kind of a summarized version of it. I know it's covering my face, but we can still, you guys, I think I can still see it. So that's really, really good. Now let's move on to see the answer. And the answer is indeed 2 over 25. So great job, everyone. And now let's move on to problem 7. Okay, now, oh, okay, it's another prime problem. Interesting. Now it says let x be the prime number less than 100, and for what value of x is the sum of the digits of x the greatest? Now, if you guys are pretty familiar with your primes, you might jump in directly and go 97. It's the biggest prime that's less than 100, so therefore it must be the correct answer. Isn't this right, Thomas?
Well, actually, this is like a gamble because since 97 it has like big digits, 9 on the tens digit, 7 on the ones digit. Like it seems that if you add the two digits, you will get a large number. I mean, and the largest number you can get is 99. And the digits, the sum of those digits are 9 plus 9 equals 18, which is the largest you can get in any two-digit number. And 97 is only two away, so but to be absolutely sure, you have to make sure that 97 is has like a digit sum that's greater than all the other primes that are smaller than it. So that would include the primes that start with 8 and end in something like 80 something and 70 something. So, 79 would be a number that could contest 97's winner place. Or maybe if I could find 80 something prime that's even bigger, say 80. Okay, so 9 plus 7 equals 16. So 88 and above would be able to contest that. So 89. Okay, 89 has a sum of 17. So 89 would have a larger digit sum than 97. So I would have to check that there's nothing greater than 89. And if there isn't, then I'll be fine. Okay, so how do I check that? There's actually a trick. So in the 90s, the greatest one is 97. In the 80s, the greatest one is 17. This is easy to check. And then once you get to the 7, the 70s, all the numbers that start with 7 and end with something, the largest sum they can have is 7 plus 9. which is 16, which is already less than 17. So I do not need to consider all the 70s, 60s, 50s, 40s, and so on. And like this is sort of like an optimized way of doing casework. And then, well, in the end, you can be sure that 89 is going to be the largest prime with the largest sum of digits.
Okay, so it looks like our final answer is 89, which so many of you guys have been saying in chat, and it indeed is the answer. So, quick round of applause to everyone who solved it and everyone who participated, because let's be honest, the real reward is in the journey and not the answer, even though it sometimes might seem like it. Okay, now on to problem number 9. And wait, hey, answer is 89, ends in 9, and we're about to go to number 9. Very, very interesting. Okay. Ooh, okay. So now we're moving on from kind of like an algebra-y kind of thing into improbability-ish into geometry. And the question asks, a regular hexagon has the same perimeter as an equilateral triangle with area 144. What is the area of the hexagon? All right. So I'm just going to quickly draw out an equilateral triangle for you guys. And let's say that the side length of the equilateral triangle is S. Then this part would be S over 2, and the height would be S root 3 over 2. Now, this comes from the fact that an equilateral triangle, or this kind of right triangle, is a 30, 60, 90 degree triangle. And so I think most of you guys have probably already memorized the side lengths. And so this is where you kind of get it from. And now, assuming that S is the side length of the equilateral triangle here, we can actually solve for S. So we have our generic formula, which is S squared over S squared times root 3 over 4, which is equal to 144. From here, we can see that S squared root 3 is equal to 144 times 4 or equal to 256. Wait, no, I think I did that wrong. My bad, guys. Oopsies, just a little blunder. We've got 144 times 4 is actually equal to 576. So I did get the sixth part wrong. Or no, sixth part right. My bad, guys. Okay, so now we have S squared times root 3 is equal to 576. But I don't really want to divide by root 3 because it's going to make things kind of complicated. So instead, we're going to leave this here for now and we're going to take a look at the hexagon. So, Thomas, do you want to help us with the hexagon part?
I mean, once you know equilateral, hexagon isn't that hard because hexagon is just six equilaterals. And that's what we're gonna play off. So, uh, if you don't remember the area formula for hexagon, that's okay because it's just six equilateral triangles. All right, so what Gloria did really nice of her was give us the formulas for area of the equilateral triangle. So if the side length of an equilateral triangle is s, then the area is square root 3 times s squared divided by 4. And currently it's 144. So this is our condition. We want to use it, but we don't want to explicitly calculate s because we don't want to carry a bunch of irrational numbers around because that's going to become burdensome. Okay, now okay, so suppose your hexagon has a side length of A. Okay, then what would the area be? The area would be 6 times an equilateral triangle with area A, with side length A. So 6 times square root 3 over 4 times A squared. This is gonna be 3 square root 3 over 2 A squared. Okay, and then what's the perimeter of a hexagon? Well, the perimeter of a regular hexagon is just 6 times the side length. So perimeter is 6a. Now, let's look at what the problem has given us. Our regular hexagon has the same perimeter as the equilateral triangle. So actually, 6a equals 3s. Okay, so now the relationship between a and s has become clear. So the way to proceed from here is I express a in terms of s, and then I express the area of the hexagon in terms of the area of my equilateral triangle here. And then I'll completely just plug in 144 to get everything. So Gloria, what's next?
All right. So, I may have gotten a little too excited over here, but that's fine. So, let's look back into this small corner of the screen. So, while Thomas did A, I used X to denote the side length of the hexagon. So, note that there's a very key part of this problem in which the problem says that or not the area, but the perimeter of both the equilateral triangle and the hexagon, they're equal. So since we already said that the side length of the equilateral triangle was S, and we know that the perimeter of a triangle or our triangle in this case is 3S, we can write 6x for the hexagon is equal to 3s, which we see down here. And some quick division tells us that x is equal to s over 2. So that's the side length of our hexagon. Now, we can actually find the area of our hexagon by splitting our hexagon into 6 equilateral triangles like you see here. So basically, just imagine it's a pizza and you're just gonna cut it 6 ways. Now we can plug in our equation. We know the area of a single equilateral triangle from up here, but now we just have to make sure that the side lengths match the side lengths of the hexagon and that we multiply by 6 to get 6 times s over 2 squared times root 3 over 4. Now, some quick simplification tells us that we get 6 times s squared times root 3 over 16. But we can also cancel out common factors, namely 2, to get 3s squared times root 3 over 8. Now, what this does is we already know s squared times root 3 from up here, right? We know that it's 576, so we can plug it back in. Now, once we plugged it back in, what do we do, Thomas?
Well, I mean, now it's just a question of calculating a fraction in the form of 3 times 576 over 8. And now that you're here, I mean, why not just do long division? I mean, I'm pretty sure 576 is gonna be like it's gonna be like a factor of 8. So you're going to get like an integer. There's not a lot of room on my screen, but we can just try this long division, make sure it works out. So 8 and then 576. Okay, I don't know, 56 is 8 times 7, and then that's 72. Okay, so 72. 576 divided by 8, 72. Multiply by 3, so 72 times 3, which is 6, and then 216. So the answer should be 216. But actually, if you're like doing this competition in real time, you can speed up these calculations by making them mental. So I mean, it would go like this. So since the hexagon and equilateral triangle have the same perimeter, the hexagon has half the side length of the equilateral triangle, which is actually just a equals s over 2. So hexagon has half the side length of equilateral triangle. This means if I split hexagon, so said hexagon, into 6 equilateral triangles, each equilateral triangle is 1/4 the area of the big equilateral triangle. So we just do 144 divided by 4 times 6. Okay, let's make sure that works out. So 100, that's 25, 11. Okay, 25, 11. 36 times 6. Okay, 6. 3, yeah, 216. So yeah, it works out. So there's many ways to do this, but as long as you get your correct answer, I'm sure they're all fine. Okay, indeed, 216. All right, what's next?
Okay, so problem 11, and that's a kind of scary, huge block of text or chunk of text, whatever you want to call it. So let's quickly read through it and see what we can get from it, like what information we can pull out. So it says that Pharaoh is riding up and down the Nile River in his barge, which travels at a constant speed of 10 miles per hour relative to the river's current. It takes them 3 hours to travel upstream from Cat City to Pyramidopolis, but it only takes them 1 hour to travel back along the same path from Pyramidopolis to Cat City going downstream. Given that the river's current is constant, how many miles per hour is its speed? So right away, there are some key points that jump out at me. And that's one, his ship or his barge travels at a constant speed of 10 miles per hour. And that's pretty important. The next one is that it takes them 3 hours to travel upstream or against the current. and then only 1 hour to travel downstream or with the current. Now, given that the river's current is constant, we need to figure out how fast the river is going. So right away, I'm going to create some equations. And this is coming from the general equation distance equals rate times time, or simply simplified, d equals RT. So what it's saying is that if you take the amount of time that you're spending on something and you multiply it by the speed you're doing it or whatnot, then you get the total distance. So if I'm walking at 5 miles per hour for an hour, then I'm going to be walking 5 miles, right? That's how far I've walked or traveled. So let's apply the same constant here. All right, but Thomas, I think I'm running into a problem here. We know the speed and we know some of the times, right? But I don't see a distance here. How can we proceed without a distance?
Hmm. So actually, this is why variables are so useful because whenever you don't know something, you should make it a variable. Okay, so I mean, look at this big word problem. In essence, it's just a play between equations and variables. So if you're able to clarify what the equations are and what the variables are, you just really need to solve them, and then it just becomes an algebraic problem. Okay, so let's look at this. First of all, one really explicit variable is what the problem wants me to solve for. So the miles per hour that the river's current is, that's our first variable. Well, here I drew a little small diagram. So in my diagram, x is going to represent the river's speed. X is flowing in this, the river is flowing in this direction. This location is P, which is Pyramid Up, however you pronounce that. And then C is Cat City. Okay, so the river flows in this direction because when I have to travel from C to P, it's upstream. So X is the first variable. The second variable, it's not so explicit. It's actually there's probably more than one way you could create a second variable, but the way I like to do it is, well, they gave us speed and they gave us time, so it's only natural that I put distance. I put distance. Like the only element I'm missing in that triangle is distance. So if I let S be the distance from P to C, like in miles, then I'll get two relationships for the times. So it takes 3 hours for me to travel upstream from C to B. So if I travel against the current, I need 3 hours to travel a distance of S. So what that means is S over 10 minus X must equal 3. Okay, and then here we should note that X is probably smaller than 10 because if your boat's speed isn't enough to outrun the river speed, then you're just gonna get dragged along by the river and you'll never reach P. So we can assume that X is less than 10. Okay, and then it takes 1 hour for you to travel the distance when you're going with the river, when you're going with the flow. So S over 10 plus X equals 1. And then actually these relations are all just distance divided by speed equals time. It's just this relationship, so it's not really mystical. And then okay, now it's two variables, two equations. I mean, we should note that this is not a linear system of equations, but we can still solve it. I mean, and one way I see that we can do it is we divide. Okay, where are my two equations? Yes, we take s plus 10x over 1, s over 10 minus x equals 3. We divide the two equations, and then we can get, say, 10 minus x over 10 plus x equals 1 over 3. And then once you cross multiply, it's just an equation in x, and then you get x equals 5. So, I mean, as long as you knew where to introduce a second variable, this problem becomes algebraic and it's kind of easy to solve from there.
Yeah, so thankfully we figured out how fast the river is, and yay! Okay, so we know it's 5 miles per hour, but let's see if it truly is 5 miles per hour. And a quick look at the answer tells us it is indeed 5 miles per hour. And as a reward for getting this awesome question correct, you guys will now be able to hear a really, really awesome fact. And the fact is, denial is not just a river in Egypt. So, denial is not just a river in Egypt. Okay, all right. Next question. All right. Okay, number 13. All right. Still kind of a pretty huge chunk of text, but it's not as big as the former one or the Nile one, right? Okay, so in a particular arithmetic sequence of positive integers with common difference d, there are three consecutive terms that can also be represented as a geometric sequence with common ratio r without changing the order of the terms. What is the sum of all distinct possible values of r minus d? So this is a little confusing. So let me just sum it up for you. We have an arithmetic sequence. So let's say we have a, right? Let's say we have a minus d, a, and then a plus d. And that's our arithmetic sequence. But also, for some three terms in the arithmetic sequence, it says that they also differ by a common ratio of r. So what that means is that a times a minus d, if we multiply that by r, we can also get A. And if we multiply A by R, we can also get A plus D. And now it's asking what R minus D is. So, okay, Thomas, I like see this relationship between the numbers and like the ratios and differences, but so when we're solving problems, we want equations. But I'm not seeing any equations anywhere, and this is like a huge problem. So how can we fix it?
Hmm. Well, actually, I think Gloria, you did a really good job. So our equations, okay, so equations come in a lot of forms and varieties, and only really rarely do you ever get a really explicit equation with exact numbers and relations. So here we have to like you have to really understand all the relationships here, and you have to transform them into stuff that you can use in equations. So think about this. You have an arithmetic sequence of positive integers with common difference d. Hmm. Well, that means that my three terms can be expressed in the form. So note that it's in the form. You don't really have to express it in this form, but you can because it's convenient. So I can express my three integers in the form of a minus d, a, and a plus d because that's what it means to be an arithmetic sequence. It just means that the difference between these two equals the difference between these two equals my common difference, which is d. Okay, so that's for arithmetic sequence. Now, what do I do with geometric sequence? Well, think about this. Geometric sequence means that you can write your three terms as we're going to use another variable now. So b over r, b, and b times r. Again, you do not have to write it like this. This is just the form that you can choose to write it as so that it becomes more convenient. Okay, so uh, you can write it in the form b over r, b, and b times r. Okay, so uh, and these three terms are all the same. So that means a minus d must equal b over r, a must equals b, and a plus d must equals b over r. I mean, technically, I mean that's like three equations. Uh, a minus d equals b over r, a equals b, a plus d equals b over r. But we don't really want to go down that path because it's not sure what you'll get if you solve that. So what you really want to do is, uh, we want to use this equation. We want to transform it into something that's easier. So notice that b over r times br just equals b squared. So now I'm gonna use the terms from here and then I'm gonna plug it in. So b over r is just a minus d, and then b times r is just a plus d, and this thing actually equals a squared. Okay, so if we look at Gloria's screen, you will get a square minus d square equals a square. So that's 0 equals negative d square. Okay, and then so d square must equal 0 and d must equal 0. And actually, this is a really cool fact because if three terms in that order are both arithmetic and geometric, they must be all constant. So that means d equals 0, and a consequence of d being equal to 0 is that r equals 1. So well, it's not really the sum of all distinct possible values of r minus d, since r minus d only has one value, which is 1. So the answer is 1.
Yeah. Or yay. Yeah. And so some of you guys might have been a little confused on how we got that equation. So I kind of just wrote it out for you. So we got A is divided or over A minus D is equal to A plus D over A. And this is because we already know that A minus D times R is A and A times R is A plus D. And so they have this common ratio R. And since both of these are equal to R, we can equate them. And then from there, we multiply both sides of the equation by the denominator to get this peak equation over here. And some quick simplifying tells us, just like Thomas said, d equals 0. And exactly like he said, a consequence of that is our sequence becomes all a's. It's just a, it's the same number, repeating. And so the same number times what equals the same number? It's 1, right? A times 1 is A. And so R becomes 1. And so, like Thomas said, R minus D is 1 minus 0, which gives us our final answer of 1. So let's take a quick look at the answer key and see if we got it. Fingers crossed. And yes, okay, this one, it looks like our answer was indeed the one. Really, really good. Yeah. Okay. All right. All right. No reaction. That's fine. That's fine, guys. All right. Next one. Oh, okay. So now we're moving on from just geometry to fancier geometry with coordinates. Okay, so unit square ABCD lies in the XY plane with A equals 0, 1, B equals 1, 1, C equals 1, 0, and D equals 0, 0. It is then rotated 30 degrees. I assume it's 30 degrees. 30 degrees counterclockwise about point A to form a square A B prime C prime D prime, which is equal to AEFG. What is the sum of the x and y coordinates of points E, F, and G? Okay, wait, I'm gonna assume that like the B prime, C prime, and D prime here was just a typo because we don't really have any primes here. So just read this as A, B, C, D. I think that's what it's supposed to say, but there's just a small typo. Okay. All right. So let's first just kind of draw a quick little sketch to get a general idea of what our diagram looks like. So using my 10 out of 10 absolute art skills, 10 out of 10 art skills, I'm going to draw my ABCD square, which is lying right over here. And now we need to rotate it 30 degrees counterclockwise. And so I can easily do that by turning it 30 degrees clockwise, and I'm gonna now draw in a yellow. So note that this diagram is very much not to scale because it's more like a 40 degrees turn. But regardless, the intent is still behind there. And so now we want to find the sum of the x and y coordinates of points E, F, and G. Or essentially just Oh, oops. Wait, I read that wrong. It says that, see, reading is really, really important skill, guys. You guys should never, ever, not read things carefully. So it says we're rotating it 30 degrees counterclockwise about point A. And so point A is this point here. So now, now our diagram is going to look something more like this. Which I don't think it's to scale, but it's just a diagram, guys. All right, so we've rotated it and we used to have this green square, but now thanks to our rotation, we have a yellow square. And well, oh, okay, Thomas, I'm stuck, right? I drew the diagram. I have like a basic idea, but they're coordinates. How can I find the coordinates?
Okay, so actually, this is what makes it, well, this is the main difficulty of the problem. So, I mean, most people, they can understand what's going on. So basically, you just take a square, you take a nail, punch it in at A, and then you rotate it 30 degrees. I mean, my first reflex, my first reflex, I mean, if I had like a CAS system, a calculator system, maybe I can just like, this is 30, this is 30, this is an isosceles triangle 1. Okay, so I could, I could with some difficulty solve for the exact coordinates of G. Same goes for E and maybe for F. But my doubts here are that, well, first of all, it's going to be burdensome. And second of all, it may end up like there may be a lot of irrational parts stuffed in there. And then they may only cancel out after I add. So, is there another way to like calculate the sum of the x and y coordinates of E, F, and G? So let's think about that. 30, 30, and 30. Well, let's just okay. So first of all, let's just investigate our isosceles triangle that has 1, 1, 1. Is it really that scary? So 30. Okay, and then since it's isosceles, the other angles down here are going to be 75, 75, 15. Well, actually does that does seem kind of scary. So because to calculate the coordinates of G, I would have to calculate the length of this and the length of this. And in a triangle with acute in a right triangle with acute angle 15, the sines and cosines or the ratios between sides aren't exactly pretty. Hmm. Okay, so maybe I need to do it a different way. What about midpoints? So if I were to connect E and F, well, let's just first of all, let's just express the coordinates x, e, y, e, uh, x, f, y, f, x, g, y, g. So I need to calculate essentially x, e plus y, e plus x, f plus y, f plus x, g plus y, g. So let's just write that out. Plus xf plus yf plus xg plus yg. Essentially, I just want to know if it's possible to do this without knowing what xe, ye, xf, yf, xg, yg would be. Because if the problem just wanted me to solve for all of this, essentially there would be like it would just be pure calculation, and that would be pointless. Okay, so xe plus xf and then ye plus yf. Hmm. Actually, I could do this if I knew the midpoint of E and F. Is the midpoint easier to calculate? Is the midpoint between E and G easier to calculate? What do you think, Gloria?
Hmm. The midpoint between E and G. So I haven't labeled all the coordinates here, so it might be a little hard to see. But essentially, the midpoints between E and G is going to be, so this is going to be E and G, our diagonal, right? So this one. And our midpoint is going to be right somewhere about here. But there's a very curious property about the midpoint, and it's that the midpoint is exactly where AF intersects it. Ooh, okay. It looks like we have something really, really interesting now. So we know that the midpoint of the line is always going to be the sum of the x coordinates of the 2 points divided by 2 and the y coordinates divided by 2. So the sum, so technically this coordinate right over here would be the x coordinates of a and f divided by 2, which is equal to the sum of the x coordinates of e and g divided by 2. And the y coordinate of the midpoint would be equal to the y coordinate of a and f divided by 2, as well as g and e divided by 2. Okay, so I think we see a very, very interesting relationship here. And, well, that's all I see. Okay, that's the problem. Thomas, I really think I'm stuck again. We see a really, really interesting relationship, but how can we capitalize on it? We know that A is 0, 1, but it seems like the problem comes from not knowing the coordinates of F, D, and E.
Hmm. Okay, yes. So we attempted to like sort of bypass actually the main difficulty we're facing. So, and this is like kind of a pretty big difficulty because in essence, what we do not want to do is, we do not want to deal with isosceles triangles with the, what is that angle? I'm just gonna call it the top angle, with top angle 30, because we do not know very much about that triangle. The angles aren't nice, and there's 75 degrees at the two bottoms. So, well, is the midpoint? Let's look at the midpoint. Is the midpoint gonna allow me to bypass that difficulty? So, okay, how would I calculate the midpoint of E and G? Hmm. Well, the midpoint of E and G was just the midpoint of D and B. The midpoint of D and B rotated 30 degrees. But that doesn't change anything for me because I to calculate the midpoint of E and G from the midpoint of B and D, I would still have to calculate that rotation. Uh, I mean, it is possible to calculate the rotation. I mean, but this is not something that probably middle schoolers know. It's called the rotation matrix, and I could brute force this right now, but uh, maybe we want to find some other method. Hey, but
Yeah.
it is possible
Oh,
in all entirety. It is possible if you just calculate everything using using a rotation matrix. You just get everything, the exact expressions, and you just add them together. I'm sure they might cancel out, but I think maybe the challenge here is trying not to do that. So let's explore something else. Okay. Let's explore the relationships between our coordinates. So E, F, and G. All right. Since we have this, okay, uh my plot is getting kind of messy. So give me a second to redraw it so I can show what I'm talking about.
yeah. So while Thomas is redrawing his plot, I can take over just really quickly. I know you guys love Thomas, but I'm sure I'm not bad either. So we have our 10 out of 10 coordinate system with our little rectangular squares. Yeah, that's the word, squares. And so I see a lot of you guys already saying, unfortunately, calculus is really, really challenging, but one thing that we can notice is that if we drop an altitude from E onto A and B, well, that creates a 30, 60, 90 triangle. And what we know about 30, 60, 90 triangles is that the sides have a really, really awesome relationship that you can see right here. So if we look at triangle A, E, and then this little, altitude over here, is that A and E has a side length of 1. So the altitude is just 1 over 2 because we're scaling essentially this triangle down by 1. So we know that this part has an altitude of 1 over 2, but we also know that the altitude of AD is 1, right? So totally E's y coordinate is going to be 1 plus y over 1 over 2. And so some of you guys might be a little confused as to why this is happening. And it's purely because this little white line here is the altitude. Because it's the altitude, right? It's perpendicular to this yellow line, which is parallel to this green line down here. And so we can essentially just build on. So we know that E is something 3 over 2. But we also know that this distance over here, yeah, right over here, right? That's just root 3 over 2. And so that we get from our triangle. And so now we know what E is. But we can do something really similar with G down here. And it's by dropping another altitude. So this time we're dropping another altitude to the y-axis. And similar, right? Similar like how we just did, we know that AG, let me label it so it's not too confusing. So this is G, and we know that AG is 1. So the height, similar to how we just did it, using the green triangle, we can see that we need to scale it down by 1/2, right? So this height is now 1 over 2, and this height is root 3 over 2. So we know that G has a x coordinate of 1 over 2, but the challenging part kind of comes from the y coordinate. But thankfully, we know that AD, right? This yellow tall part is 1. And if we subtract this part, which is root 3 over 2, we get the y coordinate of G. And so we know that G has a y coordinate of 1 minus root 3 over 2. All right, but now I think we can solve for the midpoint. So we know that the midpoint, since I'm so original, I'm just gonna call that point M. So now we're going to say that we know that M is equal to E plus G over 2. E plus G, for their x coordinates at least, is root 3 plus 1 over 2. If we divide that by 2, we get root 3 plus 1 over 4. Now let's look at their y coordinates. The y coordinates of E and G are 5. 5 minus root 3 over 2 because we can't forget about the one here, right? But actually, you also have to remember to further divide by 2. So instead of 5 minus root 3 over 2, we have 5 minus root 3 over 4. Okay, so Thomas, we know the midpoint, right? How can we find the sum of the y coordinates of points E, F, and G? Because last time I checked, M is just the sum of the coordinates kind of E and G divided by 2.
Hmm. Okay. Yeah, so what I was trying to say, once you like sort of okay, we got rid of A, B, C, D because it was kind of distracting. Uh, but you actually don't need it. It's irrelevant. So if we only look at the square, A, E, F, G, if you look at it, it's actually like the reason why it's so hard to calculate the coordinates or do calculations with the coordinates of this square is because it's tilted. There is a 30-degree tilt in it. Actually, we can actually fix this by sort of, well, in some sense, you can sort of straighten it out by using these perpendicular lines to sort of transform it into a rectangle. Okay, so first reason, why would I draw these perpendicular lines? Well, the answer is of because the tilt is really special. It's 30 degrees. And 30 degrees is something that can be calculated because we know the ratios of the side lengths of right triangles that have acute angle 30 because 30, 60, 90, well, that's just going to be 1, screw 3, and 2. Okay, so, well, I know the side lengths here are 1, and then these are all the four the four right triangles here, they're all 30-degree right triangles. So actually I know all the lengths here. Uh that that would actually like just using just looking at it graphically, I can actually uh get my coordinates real quick. So x e I mean, let's just do it. Okay. E, the coordinates of E. So the x coordinate of E is just a coordinate of A plus, well, this is gonna be 1/2 square root 3 over 2. Okay, for convenience, we're just gonna do, if this is 1, this is 30 degrees, this is A and this is B. So A is just 1/2 and B is square root 3 over 2. Okay, so E is gonna be uh no, B. Actually, yeah, that's confusing. Let's just switch A and B. So this is B and this is A because I like A to be in the x coordinate. Okay, so it's A and then 1 plus B. Okay, E down. F. Let's do F. Okay, F. Well, F, actually, I can't directly calculate F, but I can calculate F if I use E coordinate, if I use the coordinates of E, since there's just the right triangle squished in between them. So F is gonna be, well, X coordinate of E plus B. So A plus B, and then, uh, that's a what? That's a A, yeah. So A plus B and then A. Okay, and then G. What's G? G is just G it's just the A's x coordinate plus yeah, that's B, and then A's y coordinate minus the A. So that's gonna be 1 minus A. Okay, so yeah, I think I have everything, so I just need to add. Okay, so originally I was dealing with the main difficulty was I didn't know what they were. Now I do. So it's just really simple. I just add them. Okay, A plus B plus B. First of all, we can do sort of canceling. This A cancels out. In the end, it's just gonna be, that's what, 2A. I'm gonna cancel these out since I counted for it. Plus 3B plus 1. Okay. Well, I know B is actually 3 over, B is 1/2 because B is this side. That's 1/2. 3 over 2. And then A is probably, A is A is square root 3 over 2. So that's gonna be square root 3. Hmm. Okay, Gloria, what do you think?
Hmm, I think that was a really, really awesome idea, right? And so there is a lot of potential. And so if we even further work on it, because just like what Thomas did, right, we're adding up the coordinates. And so we can see that we have coordinates E and G, right, from our 30, 60, 90-degree triangle theorems. And M, right, which is the midpoint of them, if you guys know from the midpoint theorem, is simply the sum of their coordinates divided by 2. But m is also the sum of the coordinates of a and f divided by 2, because m lies on the intersection of the diagonals of the square. Now, basically what we can do is okay, so for now I'm going to slightly minimize chat. Sorry guys, I need a little bit more space. But you guys are doing really, really awesome. So I'm going to slightly minimize chat, and essentially what we can do is we can multiply m by 2. And you guys might be wondering, why are we doing that? Well, if we multiply m by 2, we essentially are adding up all of the coordinates of square AGEF and dividing it by 2. So we multiply it by another 2, or essentially we multiply m by 4, right? So we know that m, once multiplied by 4, would be root 3 plus 1 and 5 minus root 3. Now, we can just add them. And like so many of you guys are saying in chat, it looks like our answer is 6. But wait, there's a really, really, really small key point that we kind of forgot. Well, almost forgot. And it's only asking for the points of E, F, and G. 6 actually includes some of the coordinates of A, which is something that we don't want. And we know from the problem that A is 0, 1. So really, we just subtract 1 by 6 from 6, so 6 minus 1, to get the actual answer of 5. So I know this problem was kind of confusing, so I'm just going to quickly run through it and give you guys kind of the basic outline of how we approached it. So the first one was to draw the diagram. We drew a diagram that was kind of correct, maybe not to scale, but relatively correct. Next, we began looking at the information provided, and we used the 30-degree angle to create triangles by dropping altitudes, by creating heights, like you can see here in this triangle, AE, and then this height, and then we have an AG, and this height over here. And so through that, we can figure out the coordinates of E and G by using the properties of a 30, 60, 90-degree triangle. Now, we're going to draw some lines connecting E and G to A and F. And at their intersection, we can see that it's the midpoint of both AF and EG. And by using the midpoint theorem, we realize that M is just the sum of the coordinates of E and G divided by 2, or the sum of the coordinates of F and A divided by 2. And so, right, if we add the M's together, if we do 2M, let's say, yeah, let's do 2M, then we technically have the sum of F, and G divided by 2, the sum of their coordinates divided by 2. But we don't want the sum of the coordinates divided by 2. We just want the sum of the coordinates. And so now we multiply by 2 again, right? So our 2M becomes a 4M, which you see down here. And that just gives us the sum of all the coordinates of A, F, G. And quickly adding the coordinates together, the x and y coordinates, we get root 3 plus 1 plus 5 minus root 3, or 6. But there's a really small part that MacBook put in, which is really, really tricky. And it's that we only want the coordinates of points E, F, and G, not A. Or A's here. Yeah, this is A. And 6, which we just got, includes the sum of the coordinates of A. Thankfully, we do know the coordinate of A, which is given to us in the problem, 0, 1. So quickly, before time runs out, or it has already run out, but regardless, we all love math, so we're completely fine with staying over time, right? So we do 6 minus 1 to get 5. And so a quick look into the answer tells us 5 is indeed correct, and it's the perfect answer because we have answer 5 for problem 15. Okay, all right, so so time has run out. And yeah, thank you guys so much for coming today. It was really, really fun solving with everyone. But I think this is now when our live stream ends. So thank you guys for coming and bye.
Bye, everyone.